is 1. And so that's x to the 1/3. Most books will write that as the cube root. I tend to like these roots. All right, now I'm going to try to switch back to the graph and look at these. So I have x cubed plus 2 and x minus 2 cube root. So come back here. Okay, it did switch over to the graph. So x cubed plus 2 is my initial function. I'm going to zoom in a little bit on that. So now notice this hiccup. There's no horizontal line here. It's curving all the way in there. It's just a tight curve. And there's its mirror with x minus 2 to the 1/3. It mirrors that, including the little hiccup there. And we have a good function. And its inverse. So that's how we handle roots. All right, I'm going to try to switch back to the blackboard here. Got it changing there. We've got it changing here. Now we'll see if it's like Schrodinger's cat. I'll double check. Did it flip back on me? Okay, we're still a blank blackboard. So the thing to watch is if we have powers, you're going to get the inverted root on them, which means that we have to sometimes watch for domain restrictions that might pop up. All right, I'm going to look at f of x equals x plus 2 squared. All right, so from our study of quadratics, this function looks like this. And the book actually gives a particular domain to look for, but right now I'm going to talk about y. And what we can see and what we're going to know from our answers. I'm going to peek to make sure I'm still on the blackboard. Good. All right. And so this point is -2. And so we have to pick one side of these to invert. And so the book says, hey, give us everything less than or equal to -2. We're going to have to do some type of domain limitation. Otherwise, it's not 1-to-1. So I'm going to scratch out this side here. Okay. And we're only going to look at everything on this end. So we can make it 1-to-1 for us. So the first thing we want to do here, and I'll put the domain restriction up, is x is less than or equal to 2, or -2, sorry. It's everything on this side. But let's also look at the range that we get out of this. My y value is popping out of the range. Well, it starts at 0 and goes off towards positive infinity. So x is going to be greater than or equal to 0. That means my inverse function, the thing I'm trying to make here, f of -1 of x, its domain is going to be this inverse. Right? Oops, I'm sorry, I should call that y. This is the weird thing I have with the notation here, is we usually use x for the element of either thing, and yet when we talk about these things, we talk about x and y values. I will have a tendency to put x in here no matter what, because I'm talking about what makes the range, what makes the domain. I'm trying to use x and y because that's how we see the graphs right now. But this becomes the domain for the inverse. And so the x values for my inverse grab this restriction. They're going to be greater than or equal to 0. The range becomes the domain. They flip, they share, they swap over. I'm still going to use y here, though you'll see me have a tendency to put x because it's some element that makes this thing. But for right now, since we're talking in xy graphs, I'll keep this y. It's going to look like that. It's going to take, so these two things swap. All right, well, let's do this and see what this looks like, and we'll also graph it. So I take this, and I'm going to write that with a y in it. So y equals x plus 2 squared. I'm going to swap x and y. And now I need to solve for y. Now the first thing in my way is this 2. So I have to take the square root of both sides. So I'll get x to the 1/2 equals y plus 2. But I'm stuck with a choice here. Remember, when I take square roots, I get plus or minus values. And so I need to pick the values that are going to make sure that I always get a negative number. So I'm going to need the negative values. So notice here, because I took a square root, I have to watch. Do I take plus or minus values? And because I was on the left side of this, I take the negative values. And so y equals negative x to the 1/2 minus 2. Or we can use the square root sign, whichever you like. All right, let's graph both of these and see if we have a true inverse. I'll come back to my graph. And so I had x plus 2 squared. Whoops. Typed a lot of extra stuff there. There we go. There's x plus 2 squared. And the inverse, which is the function that we drew, right? Because we studied these quadratics, it matches what we drew. And I said my inverse was x to the negative x to the 1/2 minus 2. And I wanted to take the less than negative 2 values of it. Right? So there's my x plus 2 squared, only my value is less than negative 2. And there's my negative x squared root minus 2. And notice how I get my inverse. It mirrors over the y equals x. All right, I've got 2 more examples I want to do for today. I'm going to switch back to the blackboard. Let's see if this works. Okay, it switched there. Let's clear this. Scroll down. I'm going to peek back to make sure it didn't flip back. See, every time I look, I must not be clicking on it right. Now I'm going to look at a rational function and some things we can see from a rational function. So we're going to have f of x equals 2x plus 1 x minus 1. I'm going to graph this and talk about the things that we've said on rational functions. So 2x plus 1. Let me get rid of this. Two x plus 1 over x minus 1. And so this function has to mirror in two parts, right? And so there's going to be a mirroring here. A couple things we can see from this. This has a horizontal asymptote. Right? Well, why does it have a horizontal asymptote? Well, the leading powers were the same, so the fraction of the leading coefficients, 2 over 1, creates a horizontal asymptote. And there is a horizontal asymptote at 2. That means that my domain for my inverse can't equal 2, right? This horizontal asymptote, I can't have a value there. Some horizontal asymptotes, they'll dip up above and come back across it, especially if these powers are even. But in this case, this horizontal asymptote eliminates things. It also has a vertical asymptote at 1, which means the range of my function isn't going to have a value at 1. And so what we know about rational functions, this should tell us, looking at these two behaviors, that if I have to swap those, and I'm going to go back to the blackboard, that my inverse, just from studying what we know about rational functions, the inverse is going to have some power of x over some power of x, because it needs a horizontal asymptote at 1. And it has to have a vertical asymptote at 2, so it should have that in the bottom. Right? That's just looking at everything we got from rational functions. This is just, if we break this apart and think about it, of all the things functions did and all the things the inverse has to do, it's going to look something like this. In other words, I'm giving you things to look for, to check as you're doing this. All the stuff that came before said, hey, well, this is like the stuff that came before. Let's check that. Well, let's do the work. So our domain for this is x cannot equal 1. And on our range, I have to use the x notation. I can't keep calling this y, right? Whatever the range is, it's not going to equal 2. That means our inverse, our inverse's domain x can't equal 2. And the range value, the elements of the range, can't equal 1. That's what we're going to get out of this. Okay? And so we know that by looking at these two parts. Now sometimes we can't always get the range of our initial function, but that's okay. Our inverse will tell that for us, because we'll create some inverse function and its domain restrictions will tell us about the range. In fact, when I'm looking at rational functions and I want to figure out is the horizontal asymptote, is it excluded or does it cross over it, I'll take the inverse and see if the horizontal asymptote ends up in the denominator. These are just things we can look for using these things. All right, good, I still have this. All right, so I'll take this, I'll say, I'm going to take this and replace that with y. So y equals 2x plus 1 over x minus 1. I'm going to swap x and y. So x equals 2y plus 1 over y minus 1. I want to cross multiply. So I'm going to take this times this, and I'll write this up here. X times y minus 1 equals 2y plus 1. Now solving for y here takes a little bit. Rational functions take a little bit to work their way through. So I have xy minus x equals 2y plus 1. I want to get all of the y's to one side. So I'm going to have y minus 2y. So I'm subtracting 2y from this side over to here. Whoops, and that's xy. That's xy. xy minus 2y, and I'm going to add x to both sides. Each term has a factor of y, so I'll pull that out front. And now I'll divide both sides by that. And so I get the inverse of my original function is equal to, and I'll just point up to here, x plus 1 and x minus 2. Well, I get a vertical asymptote at 2, which is what this implied, and I get a horizontal asymptote at 1, which is what this implied. So our inverting function worked for us, and we're able to reverse whatever we do. Please note, with rational functions, the solving for y usually makes multiple terms in here. You got to collect all the terms of y together and then factor it out front. Right? That's a common thing that happens with these, and it's a style that we don't do all the time. We want to do one more here.
Hi, baby.
I want to do one that combines restrictions. I had one just a second ago and I lost it. It was a fraction. Yeah. This is 76 in the textbook. I'm going to brighten up my colors. Yeah, cleared my blackboard. I'm going to go bright yellow for this. All right, so we have a function. F of x equals 2 times x plus 3 to the 2/3. And so we're going to want to talk about what happens with this function. So I'm going to graph this. Okay? Now we have to say this is squaring this, then taking the cube root. So if I square this, no matter what number I put in here, it's going to come out positive. All right, so my domain starts out as all real numbers. There's nothing I can't do in here, but the shape of this function is going to cause some issues for us. So let's graphically look at this. That's what the textbook wants us to do. So let's look at this. And so what ends up happening is the squaring works like an x squared, right? In fact, if we look at this, if I compare it to the function x plus 3 squared, right, they both have this point here. Hope we're seeing the graph. Nope, not seeing the graph. It went the other way this time. There we go, there's the graph. So here, let me turn this one off. This function here is my 2x plus 3 squared cube root, right? A fractional exponent is saying whatever you do upstairs is you're squaring or cubing, and then whatever's downstairs is the root. So this is saying I'm squaring x plus 3, then I'm taking the cube root. So from a domain standpoint, it can take every real number because I'm not taking an even number downstairs. But because I'm squaring it, everything coming out of here is going to be positive. So it inflects at the point where its vertex is. And let's compare this to x plus 3 squared. I'm going to put x plus 3 squared here. Change that to red, I hope. I'll try to change it to red. There we go. All right. And I'll make it dotted, and I'll zoom in near that vertex. So x plus 3 squared has a similar behavior. At that inflection point, at -3, it's positive values to the left, negative values to the right. So this isn't going to be one-to-one. Well, let's go back and look at the function of this and how we can see that. So when we have fractional exponents, so I'm just going to, for now, say x to m over n. A fractional exponent. That is the same as x to m, the nth root. Denominators in fractional exponents are the roots. Now, I've been saying that the whole time through the course, but I haven't given tons of things on this. This is usually a algebra, not a functions lesson. But I know a lot of people are used to doing roots with the old symbology. I like the fractions because you get the fraction rules. You can multiply and add them and subtract them. And when we do polynomial type things with them, they work nicely. But for us right now, I'm taking this to the second power. That means my range is always greater than or equal to 0. So the upstairs is telling me if I'm squaring it, and squared numbers are always positive. The downstairs is telling me what my root is. Well, I don't need any domain restrictions. But notice, in that graph, it couldn't be one-to-one. And I'll just sketch the idea here. At -3, right, it turns back up. So I have to pick values on this. And normally, if we don't have anything that we need, we'll take the positive side of things. So to invert this, we imply the domain restriction that x is all real numbers such that x is greater than or equal to -3. All right, well, let's invert it now. Now that we fought our way through it all, let's invert it. So I'm going to change this to y. Why not? No, I'll stop, sorry. And you'll see why I like fractional exponents here. And I'll switch x and y around, and now I'll solve for y. So the first thing in my way is the 2. So I'll divide both sides by 2. Well, if I want to get rid of a power, I take everything to the inverse of the power. All right, I flip the fraction over. So I get x over 2 to the 3/2. My multiplication rule of exponents says that's going to be 1, so I get y plus 3. I solve for y, I get y equals x over 2 to the 3/2 minus 3. Now, if I look at this, this is telling me that I'm cubing what's ever in here. So my answer is going to be all real numbers. But my domain is limited to only positive values because this fraction is telling me I have to take a square root. So my x has to be greater than or equal to 0. Well, if I only put positive numbers in here, I'm only going to get positive numbers out. Which means that if a positive number comes out of here, the smallest one is 0. So the smallest number I can get is -3. Well, lo and behold, I've just switched these two around. Right? This has become the range of my inverse, and this has become the domain of my inverse. So it's done what's on the tin. And we used our power rules to make it easier. The book, oddly enough, writes this problem like this. It writes it like this, but then when it gives the answer, it says y equals the square root of x2 cubed minus 3. I think that's an inconsistent notation. Even though they say the same things, you could have written the initial problem as, let me change this from y. We'll say this is the inverse function. It's a much better notation, right? Instead of y's. Yeah, no more y's. These are the inverses. F -1 of x. F -1 x. I find starting with the 2/3 and ending like this is an inconsistent notation. They seem to favor square roots, and for any other root, they move back and forth. I tend to prefer the fractional expression, and I like fractional powers because instead of saying the square root of x cubed, when I multiply this by something like that, so this mathematically is x cubed square root times the cube root of x, right? Looking at that, I'm not sure how to do the multiplications. But here, this tells me I can add my powers. And I get my power rule as is. So I have preferred this notation, the fractional notation, even when I was doing the distance formula. I would prefer to put the 1/2 outside instead of the square root for the distance formula. But it's our power rules, and our power rules come in to help us. You won't see many of those in the examples, but I wanted to look at how specifically focusing on how the domain and range change about. Because it's that flipping of the domain and range that makes all of this possible. And that's really section 2 in chapter 5. That's all it covers. And I want to tell you why we're doing this. Because we're going to jump into section 3 here, and we're going to start dealing with a beautiful set of functions, probably one of the most useful set of functions around, which are exponential models. And here's a cell. Right? Here we got a cell. And it naturally splits into 2 cells. Each of these cells can split into 2 cells. That's how we grow. It's growth. This is a growth model. It's a biological growth model. Well, there's a time it takes for a cell to split, and that time makes successive levels. So we can talk about the growth as being 2 to some number times the time. Right? Whatever the k is just telling us how fast it's going. And so here it starts at 2 to the 0, right? Because there's 1. Here it's 2 to the first if k is going to equal 1 over the t thing here, right? It's some time constant. And then here it'll be 2 squared, and so on. We can figure out how many cells or how much of this organism we have in a given amount of time. We can have 2 to some function And for right now, I'll just put the t up there on its own, right? And so it's doubling over time. And so we have some population number, some amount as a function of time. And so we're able to figure out how much things we have. And this is a very important model. That's how cells grow. It's how interest is manipulated. There are many things that use this particular model. And I think I just figured out how it's switching. My button to switch between the graph and the thing that manages everything is right next to the controls. I must be bumping it. I'll lay my controls out differently. And so these models happen a lot. Population growth, interest growth, anything that disperses outwards has what are called exponential models. Well, in many cases, you'll know the amount and you'll know the model, but you need to find the time. And right now, we have no math that gets things out of an exponent down. I don't know what it would mean to take the kth root, right? I don't know what that means. So I have to find some way of inverting this. And so these models are really important. Of all of the functions that you learn, the exponential model, especially the natural exponential, can be used, it's used as a solution for so many physical models that it is one of the more useful functions that we have. Exponentials drive statistics, they drive population growth, radioactive decay, they fall out of so many differential equations. They're probably the simplest forms to do it. So this exponential function is great. Well, we're going to need its inverse. And so we learn inverting so that we can make the inverses, so that we can go backwards here. And we're going to have to invent the inverse, because right now we don't have something that tells me how to get a variable out of the power. And so we're going to have to invent that. So the next section, we're going to build exponentials. We're going to build these cell growths. We're going to build radioactive decay rates. We're going to work on everything we can do to look at exponential models, and then we're going to figure out how to invert them. All right, that's all I have for today. Please email me questions. All the work is up on Pearson. If you want to plow your way through, if you think you're okay with exponentials, you can take the exams and be done. Otherwise, I'm going to continue doing the lectures to just work over examples. The next two lectures will be example heavy because exponential models are a lot. There are a lot of models on them, and so Thursday's lecture will be very, very heavy on models. And then in next Tuesday's lecture will be very, very large on some of the mathematics behind the models. All right, be well, be safe. Hope to see you all in person soon. Take care.